Welcome to the Coherent Laser Safety Awareness Training video. Before we begin, please note the copyright laws that govern this program. If you wish to pause this video, you may do so at any time. Introduction to Laser Hazards. Hi there. Thank you for enrolling in laser training at Coherent. We are very excited to have you. As you would be training on either a Class 3 or 4 laser that can cause serious injury, blindness, or loss of life, we would like to inform you of safety practices to make sure you are safe during and after our training. Hazards in the laser lab fall mainly in two categories: laser beam hazards and associated eye and skin safety, and non-beam hazards, which include fire, particulate, chemical, asphyxiation, biological, mechanical, and electrical types. I am here today to talk to you about those hazards and how to avoid them. At the end of the video, there will be a short quiz to make sure you understand the safety protocols that must be exercised around lasers. You must pass with at 80% or better to attend the laser training session. Sit back, take notes, and good luck on your quiz. Types of eye injuries. With any laser, the greatest safety concern is with eye protection, because a laser beam can be many thousands of times brighter than the sun. Laser exposure to the eye of only a fraction of a second can cause permanent eye damage, including blindness. The three areas of the eye that are most susceptible to laser damage are the cornea, the lens, and the retina. The cornea is a transparent tissue layer covering the front of the eye. Damage to the outer surface of the cornea may be uncomfortable and painful but will usually heal. Deeper layer corneal damage, however, can be permanent. The lens focuses light to form images on the retina. With age, the lens usually becomes cloudy and can eventually progress to opaqueness. This condition is known as a cataract. The retina is the inner lining on the back of the eye that contains photosensitive elements. A part of the retina that provides central vision is called the macula. The small depression in the center of the macula is the fovea, which provides high-resolution detailed vision. The fovea receives most of the image from the lens and gives the sharpest vision. Different wavelengths damage different parts of the eye. Wavelengths in the mid and far IR, as well as the mid-UV, affect the cornea. Near UV wavelengths that fall in the range of 315 to 390 nanometers will damage the lens. The most dangerous wavelengths to the eye are the ones that are focused onto the retina. This range is called the ocular region and includes both the visible and near-infrared range, which is 400 to 1400 nanometers. The cornea and lens have a focusing capability of 100,000 times, so it is easy to understand why even a low-power beam can produce catastrophic damage to the eye. I'd like to highlight one common misconception here. Many people believe that bright light does the most damage to the eye, but this is simply not true. As you can see from this graph, the green light is perceived to be the brightest. However, when looking at the faint appearance of light with a wavelength of 800 nanometers, you only perceive 1 to 2% of the actual beam. Higher power laser beams of light exist at even higher and lower wavelengths and are invisible altogether. The misperception of output power from a laser is one of the most reported causes of eye injury, because your eye's blinking reflex to bright light only occurs for a narrow range of the spectrum. To illustrate this hazard, the first color graph represents a uniform intensity of the visible light spectrum. Now compare this to what your eye perceives. As you can see, both ends of the spectrum fade away even though the actual intensity remains constant. Be careful. You don't necessarily see the beam that hits or blinds you. Notice in this clip that you cannot see the laser beam that is burning the marks on the metal. The light you are seeing is the glow from the heated metal. Laser classifications. Lasers are mainly classified by two factors, wavelength and power. This is because different wavelengths penetrate the skin and eyes differently, and the power determines the intensity. I mentioned earlier that you might be training on a Class 3 or a Class 4 laser. There are two types of classification systems: the Code of Federal Regulations, CFR, and the International Electrotechnical Commission, IEC. All lasers can be classified by one or both classification systems. To quickly tell which classification system was used to classify the laser, CFR classifications use Roman numerals whereas IEC uses Arabic numerals. As the two classification systems overlap, I will point out where they differentiate as I explain. The lowest class, Class 1, represents no hazard. Class 1 products represent no hazard during normal use. This class contains devices such as laser printers and compact disk drives. Class 1M laser, where M stands for magnified, is safe for all conditions of use except when passed through magnifying optics, such as microscopes and telescopes. Class 1M lasers produce large diameter beams, or beams that are divergent. The next class, Class 2, represents visible lasers. They range from 400 to 700 nanometers with up to 1 milliwatt of output power. Momentary viewing of this beam is typically not considered hazardous since the human eye will blink within 0.25 seconds when exposed to Class 2 laser light. Intentional extended viewing, however, is considered hazardous. Keep in mind that the blink reflexes vary between individuals, so you can be unintentionally viewing the beam for extended periods. A Class 2M laser is considered safe, also because of the blink reflex if not viewed through optical instruments. As with Class 1M, this applies to laser beams with a large diameter or large divergence, for which the amount of light passing through the pupil cannot exceed the limits for Class 2. The IEC has three subcategories for Class 3 lasers. They are Classes 3A, 3B and 3R. Class 3A represents visible lasers with a power range of 1 to 5 milliwatts and can only be safely viewed momentarily. This category includes high-power laser pointers, which should never be directed at a person's face for obvious reasons. Do not confuse this with the CFR Class 3A, where 3 is written out as a Roman numeral. This classification comes from the old CFR guidelines and now is categorized as IEC Class 1M or Class 2M. A Class 3B laser is hazardous if the eye is exposed directly, but diffuse reflections from matte surfaces are not harmful. The accessible emission limit, AEL, for continuous lasers in the wavelength range from 315 nanometers to far infrared is 0.5 watts. For pulse lasers between 400 and 700 nanometers, the limit is 30 millijoules. Other limits apply to other wavelengths and to ultrashort pulse lasers. Protective eyewear is typically required where direct viewing of a Class 3B laser beam may occur. Class 3B lasers must be equipped with a key switch and a safety interlock. A Class 3R laser is considered safe if handled carefully, with restricted beam viewing. With a Class 3R laser, the maximum permissible exposure, MP, can be exceeded, with a low risk of injury. Visible continuous lasers in Class 3R are limited to 5 milliwatts. For other wavelengths and for pulse lasers, other limits apply. Class 4 lasers are of the highest hazard level. Instantaneous and permanent damage can result from direct exposure, as well as from specular or diffuse reflections. You should be aware that Class 4 lasers are the most commonly used lasers in the training labs at Coherent. One aspect of the laser classification I would like you to stress is that any laser product can be classified as Class 1 if engineering control measures are utilized. So, for example, the star-cut tube SL that can easily slice through stainless steel is classified as Class 1 because the laser head is encased inside a system that will shut down if the top cover is removed. However, for training purposes in Coherent's training labs, the interlocks are often defeated, and you can be exposed to or come in contact with a Class 3 or a Class 4 laser. Safety standards and regulations. Coherent lasers comply to the American National Standards Institute, or ANSI, and Occupational Safety and Health Administration, OSHA. In addition, to address other safety concerns, we also adhere to the Code of Federal Regulations, or CFR, CDRH, CE, CSA, IEC, TUV and UL guidelines. To make sure that anyone can understand the potential hazards of the lasers and labs, Coherent has adopted universal symbols for danger, warning, caution, and notice. The danger symbol means it will cause death or injury. The warning label means it could cause death or injury. The caution label means it could cause minor or major injury. And finally, notice label means possible damage to the equipment. Those are the 4 common labels you'll see at Coherent and on any Coherent product and manual. Some systems have other warning signs like the toxic gas for excimeres. To ensure that you understand all the potential hazards on your laser system, refer to the safety section of the operator's manual for your laser system. Protective eyewear. As mentioned earlier, you will most likely be working with a Class 3 or 4 laser at Coherent. Therefore, laser safety eyewear is a crucial part of your safety. Your instructor will provide you with the correctly rated eyewear for the laser you will be working with. Before you proceed with the training, make sure that your laser safety eyewear fits you well, provides front and side protection and has no digs or scratches. Do not hesitate to ask your trainer or local laser safety officer for a replacement pair. ANSI and EN standards require that all laser protective eyewear is marked with the wavelengths and the OD, the attenuation factor, for the specified wavelengths. The difference between ANSI and EN standards is that ANSI is an American standard, whereas EN is a European standard. The standards overlap, but European standards include specifications for direct hit with the laser as well as specifications for alignment eyewear. Please be aware that EN designations, such as the LB or RB numbers, apply to eyewear sold only in Europe. The OD parameter listed on the eyewear represents the degree of protection from scattered or reflected laser beams. Depending on the OD value, a laser beam can be partially blocked, allowing the wearer to see the beam, as shown with this demonstration. On the other hand, if the OD is high enough, the eyewear can completely block the laser beam. Notice that the green beam of this Coherent Genesis laser can pass through the first lens, but completely blocked on the second. You might think that's safer, but by using such a high optical density, you run the risk of not knowing where the beam is and inadvertently crossing its path. This is where the EN 208 designations come in handy. EN 208 provides standards for alignment eyewear. The eyewear is marked with an RB value that starts at RB1 and goes up to RB5. There are numerous laser eyewear selection calculators online. Ask your instructor or LSO for recommendations. The R value provides balance between OD and visibility, protects against the beam in case of accidental exposure to the eye, allows the wearer to see the spot from the beam, reduces the power of laser beam to below Class 2 limit, 1 mW for CW. However, it is not designed for intentional direct viewing of the beam. You wouldn't guess that anyone would intentionally look directly into the beam, but it happens. EN 207 addresses such cases. You should never intentionally look directly into the beam. However, in the case of accidental exposure, EN 207 just might save your sight. The EN 207 mandates that the laser safety eyewear must maintain the indicated amount of protection during a direct hit for 10 seconds or 100 pulses at the specified wavelength and power. EN 207 compliant eyewear is marked with operating modes D, I, R or M and LB values ranging from 1 to 10. Again, there are numerous online eyewear selection tools to determine the correct eyewear for your application. But the quickest way is to ask your instructor or your local laser safety officer. Safe work practices. Let's start with some very basic tips for staying safe in a laser lab. Make sure that the laser is on a stable surface and that the beams are always parallel to the ground and below eye height. Avoid use of chairs in laser labs, as sitting may bring the height of the operator's eye into the laser beam plane. The key to staying safe is to minimize exposure. We minimize exposure by limiting the amount of time exposed, limiting the amount we are exposed and keeping a safe distance away from the laser beam. The three main terms used to talk about laser safety are maximum permissible exposure, optical density and nominal hazard zone, MPE, OD and NHC respectively. When we speak of safely viewing a laser beam, it is in terms of MPE, or maximum permissible exposure. This value represents the highest dose expressed in amount and duration of laser radiation to which a person may be exposed, without hazardous effects or adverse biological changes to or within the eye or skin. This is a graphical representation of power density versus exposure time for continuous wave. From this chart, you can see that a Class 3 laser, half a watt, at 266 nanometers has an MPE time of less than 0.1 seconds, or 1/10 of a second. If the MPE time is less than 0.1 seconds for a Class 3 laser and the human blink reflex, according to ANSI standards, is 0.25 seconds, we know we need more protection when dealing with Class 3 and 4 lasers. This is where optical density or OD comes in. The OD value commonly found on laser safety eyewear and optical filters represents the attenuation factor of the filter to the base 10. OD2 attenuates the beam by 10 to the second, or 100. OD3 attenuates the beam by 10 to the third, or 1000, OD4 is 10,000, and so on. The last term is nominal hazard zone, NHZ. NHZ refers to the distance within which the level of direct, reflected, or scattered radiation during normal operation exceeds the applicable maximum permissible exposure. In basic terms, the NHZ distance represents how far away you must be from a laser if you had no protection. With low-power lasers, this distance is usually quite small. High-power lasers, on the other hand, can exhibit an NHZ of several hundred meters. Equally as important as having proper eye protection is knowing what not to wear around lasers. Any metallic or highly reflective jewelry such as rings, earrings, necklaces, watches must be removed before working with lasers. It can reflect visible and invisible beams and scatter them in unintended areas and can cause eye or skin injury or even set the place on fire. Your eyes aren't the only things that can be affected by lasers. Your skin, the largest organ, is also at risk. Just standing by a UV laser long enough can cause sunburns. Getting in the path of the beam can cause anything from moderate to complete vaporization depending on the power of the laser. The main concerns for skin damage are the beam's penetration, exposure limits, and the size of the exposed area. To protect yourself, it is best to always stay away from the beam's path. Different wavelengths of laser light affect different layers of skin. Some lasers pass through the outer layers and damage the underlying tissue. A well-known example of that is laser hair or tattoo removal. The following graph illustrates the ability of various wavelengths to penetrate different layers of the skin. Keep in mind that the beam of any laser can burn through all skin layers if the intensity is high enough. Now that we have covered laser safety, let's talk about safety issues around lasers. Electrical, fire, asphyxiation, and chemical and mechanical hazards. Electrical. While the laser beam can burn or blind you, the electricity that is present can kill you, so let's talk about electrical safety. First, let's look at these. CE mark and UL mark in US guarantees electrical safety during intended dedicated use as long as internal components are not accessed. So don't use the system for anything else but what it's intended for, and don't open the electrical components unless it's part of your training. And then, there's water. It's common sense that water and electricity don't mix, but it's inevitable with most high-powered lasers. This is because lasers, in general, are very inefficient at generating laser power and must consume large amounts of electricity to produce a beam of light. For example, high-power lasers like the Coherent LEAP use three-phase line power at lethal voltage potentials. This generates a lot of heat. But as the lasing medium needs to be cooled continuously to laze, cool water is continuously pumped to the laser. So, if there is a water leakage inside, or anywhere near the laser system, it creates the perfect situation for an electrical hazard. So, if there is any water leakage inside the cavity or near the laser or power supply, turn off the electricity immediately by pressing the emergency stop button. Fire. Now let's talk about fire hazards. I mentioned earlier that lasers can burn or vaporize skin. If it can do that, it can burn or vaporize anything in its path. The most common fire hazards are created by using improper beam enclosures that melt or catch fire, electrical circuits shorting out, and the ignition of gases from the laser process. To minimize these risks, make sure that you are using properly rated equipment and inspect for damage regularly. It is also very important to have a fire extinguishing device near the laser equipment. Whether a fixed or handheld device, be sure that it has the correct rating and is properly sized to do the task at hand. Asphyxiation and chemical hazards. Reactions induced by lasers can cause hazardous particulate and gaseous byproducts. An example of this occurs in material processing such as laser welding, cutting, and drilling from a high-power CO2 laser like the Coherent diamond laser. The vaporized material can create potentially hazardous fumes and vapors that can lead to asphyxiation if in a closed environment. Directed ventilation safety procedures must be followed when lasers are used in this manner. For more information regarding toxicity of particulates and gaseous byproducts, consult the Safety Data Sheet, SDS, for threshold limit value, TLV, of the material you are working with. Chemical hazards can even exist within the laser itself. The excimer uses toxic gases for its lasing medium. There are other hazardous chemicals to be aware of that are found around lasers as well. Chemicals, such as acetone and methanol, which are often used for cleaning optics, are skin and eye hazards. Therefore, appropriate precautions and protective eyewear and clothing must be used when handling, storing, and disposing these chemicals. The laser doesn't necessarily need to be on for you to be exposed to hazardous material. Dust, or particulates that have settled in the system from a process can also be hazardous. It's important to know what was processed in the system before cleaning it. Mechanical labels are placed on equipment to indicate potential mechanical hazards. Some of our lasers are built inside machinery that have rapidly moving parts or gases under high pressure which pose mechanical hazards. Normally, engineering control measures, like the safety interlocks, prevent operators from being exposed to these hazards. However, during certain times during training, interlock defeats are used which leaves you at risk to potential mechanical hazards. Look for warning labels inside the machines, or better yet, ask your instructor where these hazards may be and be careful. Please note that there need not be rapidly moving parts for a mechanical hazard. Heavy tools, sharp gadgets or toxic chemicals can accidentally land on your feet. So, protect your feet by wearing comfortable fully enclosed shoes. No open-toed or open-back shoes are allowed in the labs at any time. In addition to assuring the availability of protective eyewear, in any work environment that incorporates laser technology, various administrative and engineering control measures must be employed to conform to safety regulations. Administrative control measures are work practices or behaviors to reduce the impact or severity of a hazard. Some examples of administrative control measure are the warning lights over the access doors that contain laser workstations and the standard operating procedure posters that govern safe lab conduct. All individuals working in these areas are required to learn and abide by these rules. Engineering control measures are automated safety measures engineered into the design of the lasers or the facility. The external interlock switch, which is incorporated into many of the Coherent laser product lines, when connected to a door switch, is designed to extinguish the laser beam when the room door is opened. The tinted windows you see around the building is another type of engineering control measure. They have special OD coating like the safety eyewear so people walking outside the lab don't accidentally get hit with laser beams. Coherent strongly recommends using engineering control measures whenever possible. Emergency procedures. Despite all the safety measures and precautions, emergency situations do occur. Your trainer or local laser safety officer will inform you of actions that should be taken in case of emergencies. Interactive elements. Now that you've had a chance to view this video, you're ready to take the quiz. If not, please hit the button to watch the video again. Remember, you must correctly answer 80% of the questions to receive a successful completion certificate for laser safety training. The certificate is required prior to attending any Coherent training class. For those students that plan on attending more than one laser training course, please note that the certificate is only valid for 1 year. Summary and review. The laser beam that can injure you may not be visible. Never assume the laser is off, and always wear correctly rated eye protection in the lab. To protect others that may unknowingly come into the path, minimize the beam path, and use proper beam blocking devices and barriers. Laser beams are not the only hazards in a laser lab. Fire, electrical, chemical, asphyxiation and mechanical hazards are present. Always use proper beam blocking devices, check for frayed wires, look for water leaks, study the MSDS of the chemicals and materials you will be working with, and heed the warning labels and signs on the system and in the lab area. For additional laser safety information, speak to your instructor or your company's laser safety officer. They will have more specific safety information regarding the laser you are training on, or local safety regulations. The intention of this video was to give you a basic understanding of how to create and maintain a safe laser environment. For additional information on laser safety and the terminology used, you may wish to refer to the following publications and websites. This concludes the laser safety training video. You should now have a general understanding of laser safety and the proper precautions to maintain a safe laser work environment. If you are viewing this video at Coherent and have questions or difficulties, contact your instructor that presented this video. Otherwise, contact the Coherent Product Support Hotline. Thank you for watching our safety video. We hope it was informative. If you felt we missed any laser safety topics, please let us know. We'll be sure to add it to our sequel. We can be reached at laser.training@coherent.com.